All right, so today's lesson, 3.5, we're going to talk about rational functions and their graphs. This is I would say this is pretty important as far as future math classes are concerned and future topics. So this is something that we're going to spend some actual time, like some real time going through. From that perspective, there are probably going to be several videos on this one. And again, I am going to try to keep each one of these videos to under 15 minutes. We'll see how that works. And so again, I'm assuming that there's probably going to be at least 4 of these, maybe more. We'll have to wait and see how it goes. But the problems themselves, each individual problem can take a little bit of time. So first of all, we're going to develop how we get to actually doing one of these problems. Let's talk about the actual rational function itself. A rational function, the easiest way to describe it, it is the quotient or the division of 2 polynomial functions. So it is the quotient, which is just the division of polynomial functions. And if you recall, polynomials are defined to be any function where the variables are raised to only whole number exponents. That was the polynomial function. So technically we could write this as some f of x is some polynomial function over some other polynomial function. Now polynomials, again, the whole values, the exponents can only be whole values on the variables. That being said, I want you to understand that a constant is also a polynomial. That's going to be very important. So the number 1 or the number 7 or something like that, that's also a polynomial function. So just a constant is a polynomial. Now obviously, in our case right here, q of x, which is our denominator, cannot equals 0. If q of x is 0, we're dividing by 0, and this is no longer a function. It doesn't work. Okay, so let's go ahead and start with the most important part of this thing, is we want to be able to find the domains of these polynomial functions. So we're going to find the domain of a polynomial function. The easiest way to describe this is that any value that you can plug into the denominator to make the denominator 0, it has to be eliminated from the domain. We've talked about that before in previous sections. So let's do a few examples real quick of this and just see how it works. So let's do f of x equals x squared minus 9 over x minus 3. We're going to do g of x is x over x squared minus 9, and we're going to do h of x is x plus 3 over x squared plus 9. So let's go ahead and take a look at these things excuse me, and see how it works. Alright, so let's start off with f of x equals x squared minus 9 over x minus 3. Now remember, the idea is we need to look at the denominator. The denominator is going to really help us with our domain, because whatever's in the denominator, we can't have it be 0. So we're just going to take a look at x minus 3 and say, well, okay, if I take x minus 3 and set it equal to 0, if I solve that for x, x would be 3. This has to be eliminated from the domain, because if I plug 3 back into my denominator, it's going to give me 0 in the denominator. At this point, it doesn't matter what happens in the numerator as far as the domain is concerned. X is 3 has to be eliminated from the domain. X cannot equal 3. So we'll say that x cannot equal 3. That is part of our domain. To write this in actual set notation, I'm sorry, not set notation, interval notation, we're going to write it as the domain, whoops, sorry about that. The domain is from negative infinity to 3, and then we start back up again at 3 and go to infinity. That's the domain. Okay, let's take a look at the second one. Now the second one's a little bit different in the fact that we have to do some work up front. G of x has a denominator which needs to be factored first. X squared minus 9 is the difference of perfect squares, and it factors. So we're going to rewrite this as x over x minus 3, x plus 3. And then what we're going to do is we're going to take and we're going to separate each one of those things and set them each equal to 0. And then we're going to solve each one for x. So in the first one, if we add 3 to both sides, we get that x equals 3. The second one, if we subtract 3 from both sides, we would get x equals negative 3. And those are both of the values that have to be eliminated from our domain, because both of those, if I plug those back in to my original function, it's going to make the denominator 0. So in this case, our new domain, we could say that x cannot equal plus or minus 3. We could say it that way, or we could separate that. Or we can write this in interval notation. Now remember, I have two things in the denominator that have to be eliminated, so I should have 3 intervals here. So we're going to go from negative infinity up to negative 3, because that's the first one that occurs numerically. And then we're going to start back up at negative 3 and go up to 3. And then we're going to go from 3 to infinity. And there's our domain. All right, and then our last one. X plus 3 over x squared plus 9. Well, x squared plus 9 does not factor. It's a sum of perfect squares. That is not factorable. So the only thing we can do is we can take the x squared plus 9 and we can set it equal to 0. And when we set this thing equal to 0, we're going to try and solve this. Well, again, it doesn't factor, so the only way I could try to do this is to subtract 9 on both sides, and then take the square root. And the problem with that is, if I take the square root of the left, I get x. If I take the square root of the right side, I would get the plus or minus square root of negative 9. Square root of negative 9 is going to be something which is not a real number. Therefore, nothing makes this denominator 0. This does not work. So there are no values that I can plug into x to make it 0. And if you really think about it, if I take any value and I plug it in for x in the denominator and then square it, it's going to become positive, with the exception, of course, of 0. If I plug 0 in there, 0 squared is just 0. But still, 0 plus 9 is going to be positive in the denominator. There's no issues. Anything else that I put in there is going to be a positive number plus 9. It's still going to be a positive number in the denominator. It will never equal 0. So the denominator here cannot equal 0, meaning that every possible value is going to work. So my interval here is every real number, or negative infinity to infinity, or of course our shorthand notation, the r with the extra line through it.